All right, so now today we're going to carry on with chapter 8. Specifically, we're going to look at 8.3, which is our discussion about trig integrals, they're called. And so, what we're going to do is focus our attention on two specific cases. One of them involves integrals where we have a product of the sine and the cosine with potentially different exponents. And then we'll do something similar with secants and tangents. And we'll see that the rules that we follow ultimately it will depend on whether the exponents are odd or even. Okay, so that will help us decide what rules to follow. So there is a list here somewhere. Here it is. So if you look at slide 8, they're helping us make decisions based on this setup here, where you can see that if the sine's exponent is odd, we have one rule to follow, and if the cosine's exponent is odd, we follow a different rule. Okay, and then the same thing will be true with the secant and the tangent, which you can find down here on slide 14. The rules are listed here. In this case, if the secant's exponent is even, we have one rule. If the tangent's exponent is odd, then we have another rule. Okay, so let's go back to where we were and do some examples. Okay, so now we'll start with a relatively simple case. Here we have the integral of sine to the fifth cosine x. Okay, let's try that one. So once again, it was sine to the fifth power of x cosine x dx. Now, in spite of appearances, this one probably should be managed with u substitution, our old friend u substitution, and let us try u equals, oh, let's try sine x. And then du dx is cosine x, which is the same thing as saying that du is cosine x dx. So that means what we actually have here is then u to the fifth du. Okay, so it's that straightforward. All right, but a lot of the other cases we might run into, what if the cosine had been squared, for example, or cubed? Then we would not have been able to use this approach, and we would need to try something a little bit different. So how would that work? All right, so for example, oh, by the way, I just want to mention this. There's so many trig identities. Um, they're trying to help us out here by showing us just the ones we might actually need for what we're about to do. If you were to look in the book, somewhere there's bound to be a list of all the trig identities. I'm not sure if I copied them into Brightspace or not. Uh, well, we could take a look, I suppose. I don't. Hold on one second. Let me go find Brightspace. I'm just curious to know if I might have put it in there. If not, maybe I'll go ahead and go look and see what I can do about that because the list of trig identities is so long and so massive. It's almost beyond belief how many different identities there are. So yeah, let's go in here real fast and double check. So under the category tables, maybe not. Oh well, I'll look into that. But If you look in the back of any calculus book, you'll see the list is just beyond belief how long it is. There's like double angles and there's half angles and there's all kinds of different results that we might need. So here what they're saying is, well, once you pay attention to these three, because these are the ones you might need, and so they're being very helpful here with us. And if you notice, they're all functions of either sine squared x or cosine squared x. And so these are the two that we haven't seen before, at least in this book. The first one is one of the standard Pythagorean identities. There's actually three of them, but the second and the third ones are derived from this one anyway, so they're not really unique. But these two, with a little algebraic manipulation, you can prove that these are correct as well. And so we're going to end up needing to do some substitutions as we go along, and that's why these are here. So you'll see as we go along why we need these. So here is a chart that will help us figure out what to do in these different cases. Ultimately, our decision comes down to the exponent of the sine versus the cosine. And as you can see, in the first case, as long as the sine's exponent is odd, then we can do the following. You can see what we're doing. We're reducing it a little bit. You see what they've done is they factored out the sine here. And the purpose of doing that is for the du. So here the exponent was 2k plus 1. And here it's sine squared. That's actually sine 2k. And one of them has been split off so that we can create a du. Down here, when the cosine is odd or the exponent is odd, they're going to do something similar. They're going to strip off one of them down here for use as a du term. Okay. All right. So, for example, oh, if they're both even, which we don't have that case here, then we have to use these to take care of our problem. Okay. So, anyway, let's start with this one. So, first, let's see if it fits into one of our rules. Okay. So, the sign is odd. The exponent is odd, I mean. So that looks like we're going to use this rule. Okay, great. So, what they want us to do is so we're going to have sine squared x cosine to the fourth of x sine x dx. And they're going to then oh, and by the way, this is going to require one of the Pythagorean identities. Namely, they're going to have us get rid of the sine squared x so that when we're done, we have only cosines except for this piece here. So in other words, this becomes 1 minus cosine squared x. Here's cosine to the fourth of x. Okay, now it still appears to be a bit of a mess, but we can multiply this out. Okay, so let's do that. All right. Now we can break it up into two terms, or two integrals, I should say. All right, now we can start thinking about a u substitution. Now, By the way, I do have a little chart here somewhere. Here it is. So just a quick reminder, the derivative of cosine x is negative sine x. So if I let u be cosine x, by the way, I've got to really be careful with this. I just realized this looks like 4x. It's actually meant to be cosine to the fourth power. That's better. And therefore, du would be negative sine x dx, which we don't actually have. Well, but we can provide the negative ourselves. And then over here, we can do the same thing. But that negative would need to come on the inside here because it'll be the same situation. U is cosine x du dx. Well, I guess I didn't have to write these all over again, but just a reminder. So what I'm going to do is rewrite these slightly. And now it's pretty straightforward because look what I have, minus integral u to the fourth du plus integral u to the sixth du. And now we're all set because you've got um, based on the power rule, we end up ultimately with and there we go. So the strategy, the cleverness of the strategy here coming up here, well, two things. Splitting off one of the signs and bringing it over here. And then, of course, we still need this Pythagorean identity. Otherwise, we might not recognize that we can eliminate the sine squared and replace it with a function of the cosine squared x so that at the end, we have only the one trig function in here. Okay, so that would be the final answer. So you kind of get the idea here. They're all going to work the same exact way. It's just a question of what do we split off? What do we choose for our du? And what identity do we need to simplify it? Excellent. Um, Now, here's some formulas. I guess if you're really stuck, you could try these Wallace formulas. I I don't know if that's any easier or not, but there they are if you want them. All right, so now we're going to take a shot at one of these secant and tangent integrals. And the logic is basically the same. And even secant, but what's different here is that you're splitting off not secant x, but secant squared x. Okay. Down here, though, even more interesting, you're splitting off a secant and a tangent. So it's a little bit messier than what we were just doing. But if you notice over here, they've already given us the basic formula. So, I mean, really, they've kind of already done the work for us when you look at it. Um, so, um, when we have an even powered tangent, um, what we want is to split off a tangent squared, but then immediately turn it into secant squared. So remember that tangent squared x, one of our identities, is secant squared x minus 1. That's because the original version was this. Okay, so they, of course, mean the same thing. All right, so why don't we try one of these? All right, so this should be fun. So we've got the tangent cubed. Now, which of these rules should we be using? Let's go back here. All right, it looks like it's this one because the tangent is odd. All right, let's borrow this. And what they're recommending that we do, as you can see, is rewrite this. We need to split off a secant and a tangent. Now, we don't have a secant, do we? We have a square root. So what we're going to have to do, actually, we may not use this at all. Hold on one second. Um, oh, I see what they've done. Okay, okay, yeah, okay, this will work. A little bit of manipulation. In order to split off, um, a, if we need down here, this part is easy, of course. We need a secant here, which means we have to divide. It's like we're basically multiplying and dividing by the secant. And so you're going to end up with secant minus 3 halves x here. All right. Right, because if you multiply this one by this one, it'll bring you back to secant minus 1 half x. Now, the tangent squared is going to be replaced with based on our Pythagorean identity, secant squared x minus 1. And then this, the purpose of this is to keep these together. And by the way, let's go back and look at our list of derivatives. And so you can see the derivative of the secant is the secant times the tangent. That's what this is building up to. That's why we keep setting it up this way. Looks like my handwriting got a little messy there. So in other words, when we look for u and du, this is why it's being set up this way. So, all right, so we can multiply these out. So when you multiply secant to the minus 3 halves power times secant squared, you end up with positive 1 half. All right, and then we'll, of course, split it up. All right, I got a little low on space there. So here the u is, and as we saw just a second ago, Not that the order matters, but the derivative of the secant is secant times tangent. I'll just write it like this. And over here is the same thing. We don't need to write it again. So we have here u to the 1/2 du up minus u to the minus 3/2 du. And of course, this is easy because we're just going to use the power rule. And then we can clean it up a little. And of course, remember, u is the secant. And that should do it. All right. And we're done. Very good. All right. Of course, it helps that they're showing us what, they're giving us all these hints. But you can see the idea here is just to basically, if you follow these rules correctly, it's just a question of which one should we use. Oh boy, now here they're kind of playing games with us a little bit because they're saying, this one doesn't seem to fit. Well, all right. So, just a quick reminder. So what we actually have here is, now of course this implies that tangent squared of x is the sine squared over the cosine squared. But this is 1 over tangent squared, so you've got 1 over cosine x times cosine squared of x over sine squared of x. And now we can simplify a little bit. And well, now let's see. It might, yeah, maybe not. I'll tell you what, maybe that's not the best way to go right now. Um, if we let u be the sine of x, well, that should be, all right, that looks promising because now you've got du over, oh yeah. And that in turn brings us to, and of course, u is the sine. And the inverse of the sine is the cosecant. I don't know if they expect us to do that, but let's try that. But that should take care of it. And there it is. Yeah. They did expect us to do that. That's fine. So it's negative cosecant x plus c. Beautiful. But, again, they had to throw us that little hint. We could have perused through all the rules for a while, but they decided to be helpful to us and say, this doesn't fit in with those rules. So again, it's like we need a lot of practice. Now, look at these. Um, again, like I mentioned, if you made up a list of all the different rules, it would be several pages long. So here they're helping us by saying, if you don't remember, here's some more rules you might want to use involving sines multiplied by each other or cosines or sines times cosines. All right, so with those in mind, let's see what they want us to do. Now, this one, if you notice, it's not sine to the fifth power, it's sine 5 and it's cosine 4. So in other words, those earlier rules are not applicable here. Sine 5x, cosine 4x, oops, 4x. So which one of these does this look like? It would be this one. Okay. So we could rewrite that as, so this is our M, this is our N. All right, so in other words, we have, I'll move this out here. Oh, I almost forgot the dx here. And of course, now we can just go ahead and break it up into pieces. All right. So the integral of the sine is the negative cosine. We have that list here somewhere. These are the derivatives. If you look at the integration, hmm. Oh, there it is. The integral of sine u du is just negative cosine, so we're good with that one. Okay. Actually, what we should probably do is use substitution here, because otherwise we're going to miss something. So let's try this. For this one, so the derivative of the sine is the cosine. Oh, no, I guess that's not going to work here. No, we don't want u substitution. We want u substitution over here, though. Um, hold on, let me stop. Let me fix that. Yeah, see, the problem here is that if, oh, right, I get it now. Okay, so u is x, du is d. Okay, that's what we're looking for. Over here, see, the problem is over here, we need to supply a constant. If you let u equal 9x, then the du would be 9 dx, which we don't have. All right, now we're getting somewhere. So what I've got to do is multiply by 9 and then divide by 9. And so the first term is fine the way it is. 1/18th, and then here, Now, the thing is, the definition of u is different for both of these integrals, so we have to keep an eye on that. But this one is just very simply the integral of sine u is negative cosine u, but the u is different in both cases. So this first one is just simply cosine x. Then we have negative 1/18th cosine. For this one, we chose 9x. And of course, we need the c at the end. All right. All right. So let's see how we did. Yeah, that's it. Okay, excellent. So what we had to do here was recognize, we've never seen this before, but because it's not exponents anymore, it's sine of something other than just x, 5x in this case, and 4x. We can use these rules here. I don't know if there's a name for these rules. Why, yes, there is. It's the product to sum formulas. All right, let's make a note of that. I'm sure there's plenty more, but those are the ones that I think that we might need. And so now, oh, okay. So we're ready for some of these. So we'll go back to our rules. Okay. So, oh, not those. We need cosines. So we have an odd cosine. So we need this one. Okay. So they want us to split off one of the cosines for the du, and let's rewrite it the way they're doing it. Okay. And I think the plan here is to take one of the Pythagorean identities and replace this with, okay, but because it's x is 2x, this becomes, okay, now then we can multiply these out. Oh, you know what I just realized? I goofed. We were supposed to keep the sign and no, all right, let's try that again. I just noticed that. We're keeping the sign because we had too many cosines. It's this one that's getting replaced with the Pythagorean identity, which means that cosine squared of x equals 1 minus sine squared of x. All right, that's better. Okay, now we're good. And then we can split it up, of course, into two separate integrals. All right. So this is by the chain rule, by the way. And of course, we don't have 2 cosine 2x dx. We need to supply that. So let me see what we can do. I want to keep this, I'll work on these one at a time. So what we're going to need to do is multiply and divide. And that's going to give us, so all of this is du. And so we're going to end up with u cubed over 6. And of course, u is sine cubed 2x. There it is. Oops. Let's make that a little neater. And then, of course, I need to now contend with this one. Sine to the fourth of 2x cosine 2x dx. It's the same basic thing. We're going to need, if we let u be the sine of 2x, du is 2 cosine 2x dx. So it reduces to 1/2 u to the fourth du. So we ultimately end up with 1/10 sine to the fifth 2x. And now keep in mind too, based on what we had up here, we're subtracting one from the other. So the final result is um, hold on 1 second. Um, let's go get our results. Sine cubed sine cubed 2x over 6. And then we'll add this one. Actually, we're subtracting. All right, remember that one is being subtracted from the other. Or I can write it like this. And of course, don't forget the C. All right. Wow, what a nightmare that was. So that would be, looks like it's D. Yep, it's D. Beautiful. Okay. Um, then we have one more of these. Now, this one obviously goes back to our secants and tangents, and it is, all right, so let's go back and revisit our rules. So we've got an odd secant. Oh, no. We got an odd secant and an odd tangent. I mean, one counts as an odd number. So I guess we're going to use this one. Either that, or maybe it's just straight ahead U substitution. So the derivative, hmm. Now let's follow this one. It'll be a little quicker, I think. So here's what we'll do. Um, we need, oh, see, that's interesting because it's already, we can't have two tangents here. There's only one tangent. So I guess we are going to need U substitution. So if we go back to the basic rules of differentiation, the derivative of the tangent is the secant squared. All right, so what could we do? See, the problem then is we have secant to the fourth. We don't want that. Um, maybe we could make this work. Let's do this. Let's try this. I'm going to rewrite it as, and then they want us to use one of the trig identities, one of the Pythagorean identities, which is that the secant, sorry, the tangent squared will be replaced with secant squared minus one. Oh, but it's not squared, so no, we can't do that. Oh, wait a minute. No. Hmm. The derivative of the tangent is the secant squared. But at the same time, though, the derivative, no, that's it. That's all we have. Of the secant is the secant times the tangent. Oh, okay. Maybe we're in pretty good shape after all because I think I see what we're going to do. If you let u be secant 2x, yeah, I think we're good. Okay. And that 2 is here because of the chain rule. That's the derivative of 2x. And we do have that. Okay, I think we're in pretty good shape now. Um, which so that means we have u to the fourth. We don't have the 2 though. Actually, let's supply that now. And then we can finish it up. All right, and so all of this is du. This is u to the fourth. Okay, and then we have, and of course, u we've chosen to represent secant 2x. And that should be it. Um, so we're going with, oh, I forgot the 5. Sorry, this is to the fifth. There we go. Secant fifth 2x over 10 plus c, which is b, and that is the correct answer. Okay, so we got it. Okay. Phew. Oh my God. Now, what's coming up next? Now, that was 8-3 trig integrals. And of course, the whole point of this was to use those special cases and make the correct substitutions. What's going to happen in the next section is that it's called trig substitutions. And what's happening there is that we're finding these very messy integrals, but in some cases, at least, if we make the right substitution, we can reduce them to a trig integral. So the challenge is turning these horribly messy integrals into a relatively straightforward trig integral. And you can see they're showing us some of these results that we can use, and then, of course, the Pythagorean identities. So that's what's coming up next. Now, when this is done, we're going to move into something 100% different, something called partial fractions, which is a technique that's used to help us break up messy integrals into something much more manageable. And I think you'll agree that once you get the hang of it, it's a very powerful technique and very helpful. But first, we'll move on and do the trig substitution, and then we can move on to partial fractions. So I think we'll save that all for next time. And so I'll see you then.